Hi there. Okay, so we're going to move on and look at the spherical mirror. So right at the top here, spherical mirror, to remind you that we're not just talking about flat mirrors because we've already kind of considered flat mirrors, but in this case, we're going to have a mirror that looks very similar to what we had in the lens equation and the lens case, right? But instead of putting a concave or convex lens here, we're going to put either a concave or a convex mirror here. And I'd like for you to consider what happens to the rays of light on the mirror. Let's do a concave mirror, and if we take a sphere and basically we cut out part of our sphere. So we're just going to take a single cutout from our sphere. That gives us the shape that we're looking for our spherical mirror. The optical plane for our lens was directly through the center of the lens, but the optical plane for our mirror is actually right here. But here's the basic theory behind a spherical mirror. If we are to take our rays, just like we did before, we take a ray and we bounce that ray off of the mirror, then if you were to take the center of our circle, which is located right here under the edge of the second R, and you were to mark it right there, that's the center of the mirror, see, right there, then the radius of curvature would be given by this length right here, and also would provide the normal to the surface here, right? That normal to the surface means that by the law of reflection, that this ray of light at that location should exit and go along a path this direction of equal angle to the red normal that I've drawn here. So we would then have a ray that has twice this angle. So it would be about right there. So it can be shown that all of these rays are going to do this, and all of them are going to strike a point here that is theoretically, I'm going to write another red dot here. So these are two very important red dots. One of them is the focal length of the mirror, which should make sense because it's doing the same thing that it did in the lens case, except for this time it's bouncing rather than transmitting through the lens, right? And then this one we give as capital R, the radius of curvature for our sphere that we took our piece out of to make our mirror, right? Okay, so now this is reflecting off the inside of our spherical surface here, right? And we can now see that the relationship between the radius of curvature and the focal point is then given as the focal point is exactly half the radius of curvature. That can actually be shown geometrically, but it's kind of a little bit clear here just from looking. So you may be asking, well, what equations then apply here? So the equation for the object versus image distance in our case, if we take an object and place it right here, and it's going to have, of course, an object distance from our optical plane, same as we did in the lens case. And the equation for finding the relationship between the object and image distance is 1 over the focal point is equal to 1 over the object distance plus 1 the image distance. This is the same as it was before, right? So now that's interesting because the fact that you had one equation that was strictly for light refracting through a lens happens to be the exact same geometry or at least the mathematical geometry, I should say, as that of a spherical mirror. There's a couple of things that we have to keep in mind here, though. So you may remember that in the case of our lenses, focal length was positive when we had a ray focused in on our focal point. So let's clarify what a positive focal point means and what a negative focal point means. Let's look at the lenses that we had before and compare them to the mirrors that we have now. So we have here our convex or positive lens, and we have to look at the behavior of rays of light that comes through this lens. We have here concave or negative lens, so that you can really truly get a sense of the focal points based on whether this is a positive or negative lens and where the light goes. These focal points can actually be located at the same point for both of these lenses, and if we had, say, a 15 centimeter focal length for each of these lenses, then it would just represent different action, but at the same reference point. So let's take our parallel rays and see what happens to those parallel rays, because that's what defines whether this is a positive or a negative lens. If we take a parallel ray on both, and remember by parallel ray, I mean parallel to the optical axis, right? Sometimes we say that it comes from infinitely far away. If I take this parallel ray, then for a convex lens or a positive lens, then it's going to cause this ray to focus toward this focal point, which we've already discussed. So essentially what this does is that it sets up the interfaces of glass such that it bends light toward the optical axis, okay, or at least it attempts to. It will succeed if the light that's incoming is parallel. If it's not, well, it's still going to do its best to bend it toward the optical axis. So what about the case where a concave or negative lens experiences this parallel ray? It will try to bend that ray away from the optical axis. Well, in what direction? Well, if we take this focal point and we pivot about that focal point in such a way that we encounter where that ray struck the optical plane, we get to determine then what direction that ray is carried. It's carried away from the opposite focal point. So in other words, a positive lens carries the ray toward a focal point, and a negative lens carries it away from the focal point. Now, what this means is that positive focal points take rays and combine them together, even if for only a fleeting instant. Okay? But a negative lens has a tendency to spread rays. So these incoming rays would be spread in the following directions, away from the opposite focal point. Okay? So that gives you the gist behind what it means for something to be positive or negative. Another way to think about this is that a positive lens actually focuses light together, and a negative lens just appears as though those light rays came from a focal point. So if you were out here observing this ray, this ray, this ray, and this ray, all of those actually met at a point, and then they came away from that point. Same as they did earlier when we talked about a point reflecting off of an apple. So that's why it looks like there's an image at this location. But if you're looking at these four rays, on the other hand, you would be tricked. Your eyes would be tricked. A camera would be tricked into believing that they all came from this point right here, when in fact they didn't. And that's because there appears to be an image here. The rays didn't actually come from that location. It's fake, so the focal point is on the opposite side, and we call that negative. Okay, so let's bring that back to our discussion on mirrors. Why don't we take our same circle here, and this time, instead of creating the inside surface, we'll create the outside surface, like so. Should make that darker. Okay. So this is now our new mirror, and we can see what happens in the case of our concave mirror here. We're going to get rays to focus in. If we took these same rays and the same focal point on the other type of mirror, where you can imagine this is like a shiny, polished metal ball, then the result would be a little bit different. With these incoming rays, we would be most interested in a focal point on the other side. Unlike the lenses, mirrors only have a focal point on one side. And so in this case, the focal point is where the rays actually go. And in this case, the focal point is actually where the rays appear to go. So we would place the focal point, same distance, only, oh, notice that I put that from here to here. I need to make a correction on this. I put my optical plane here. That is incorrect. I put my mirror in the wrong location here. The optical plane should in fact be right there. So they should always touch the mirror. The optical plane should always touch the mirror where the optical axis touches the mirror. Right? Okay. So the rays come in the same fashion that they did up here, but the effect is going to be different. If we look at the radial line here, still forming the normal, then well, actually the radial line here from back here would form the normal, then we can see that the rays are not going to be focused inward toward this focal point, but are instead going to be focused away from this focal point. So we would experience, this ray would experience a bouncing away, like so. This ray would experience a bouncing away along this line, and this one along this line. So, like so. That means we can also think about what that looks like those rays were coming from. I can say that it appears that those rays were actually coming from this location here, from this one. This ray looks like it's coming back from this direction, and this ray looks like it's coming back from this direction, right? So this is the general way that ray optics work for our mirrors. And if we wanted to look at objects and images in mirrors, it's really not that different than it is in the case of the lenses. We still use the lens maker's equation, and we also use the magnification equation, same as we did before. Let's write out that magnification equation. It is that the magnification is equal to, or it's actually defined as the height of the image over the height of the object, and is also equal to the negative of the image distance over the object distance. Now recall from the last video that I said Q is always positive when the image is formed where light goes, and it's always negative when the image is formed where light doesn't go. In the case of the lens, light goes through lenses, but in the case of the mirror, light actually does not go through the mirror. So in this case, if an image is formed on either one of these mirrors, if the image is formed on the same side as the object, then we would call that a positive image distance. And if it's formed on the other side, inside the mirror, essentially, we call that a negative image distance. Okay, let's look at an example. So let's take the case where we have a focal length that's actually a little bit farther out there. So what we're going to do here is each of these dots is going to be 10 centimeters. And we're going to have a focal length of a magnitude of 30 centimeters, so 3 dots out. And then we need to know, is that focal length positive or negative? Well, we don't have a concave lens, we have a convex lens. So we have to think about would this scatter light or would it bring light together? This scatters light, therefore that's a negative focal length, right? Okay, so the focal length would then exist right here at this point. All right, so given that focal length, if we had an object that was located, let's say right here at a P is equal to positive 10 centimeters, and I'm going to go ahead and make the object height also 10 centimeters. So I'll place an object right here, and I want to know where the image is going to be located. So we go through our same process. What would the image? What would be the magnification for the image? Or in other words, let's answer where is the image. Let's answer how big is the image, and let's answer right side up or upside down. Okay. So where is it? We would use our equation. So we have rearranged 1 over the focal length minus 1 over the object distance is equal to 1 over q, right? That's going to mean that we can rearrange to get q is equal to 1 over the focal length minus 1 over the object distance flipped. So we would get 1 over negative 30 minus 1 over positive 10 flipped. That gives us a negative 1 over 30 minus a negative, or not, minus a 3 over 30. So very similarly to what we had in the last video, we would have a negative 7.5 centimeter image distance. Okay, at negative 7.5 centimeters, we would say, which side is it on first? Is it on the left side of the mirror interface, or is it on the right side? Remember, image distances are negative when they exist where light doesn't go. And image distances are positive when they exist where light does go. So if light bounces off mirrors, then positive image distances are over here, negative ones are over here. So we can see that it's going to be on the right side. We have a 10 centimeter mark here. Here is a 5 centimeter mark. Here is a 7.5 centimeter mark. So we know that this is where it's going to be. X marks the spot. Now, is it going up or down, or and also is it larger or is it smaller? So looking at that magnification, we get negative q over p, which is equal to negative of, what's our q? Negative 7.5 centimeters over positive 10 centimeters, and that works out to 0.75. It's going to be 3/4 the size of our object, right? So it's going to be located here at the X, and it's going to be about 3/4 the size of the object. Okay. Okay. In our next sets of videos, we're going to use ray tracing to double check these results. So what we're going to do actually first is we're going to ray trace, and then we're going to calculate and see how close we are to our ray trace. Okay.